Let's do topic 2, singular matrix and latent roots. I don't know the meaning of latent. It's reminding me of India's Got Latent. Anyways, so step 1, what is a determinant? You need this first. I remember calculating determinant actually, but okay, I'll read it. The determinant is just a one single number you calculate from a square matrix. It tells you tells you important stuff about the matrix, like whether it's singular. Coming up next, I forgot what is a singular matrix. Anyway, so for 2 by 2 matrix, we just multiply it diagonally crosswise and subtract. So for this, we are going to multiply AD minus BC, as you can see in the example. And for the 3 by 3 matrix, it's a bit longer, but same idea. Expand along the first row. So we expand along one row and pattern take each number in the top. For example, A. Multiply it by the determinant of 2 by 2 box after deleting its row and column with the alternate sign. So if we are like doing it for A, then we forget about this part and we multiply A with this determinant of this 2 by 2 matrix. What is a singular matrix? Let's see. Simple. A matrix is singular if its determinant is 0. So if determinant is not equal to 0, it's called non-singular. That's the whole definition, nothing more to it. But why was it important to know? Maybe it showed that solution exists or not, or something like that. Anyway, so step 3, what are latent root or characteristic roots? So these are just fancy names, lol, for the same thing. You might also hear eigenvalues. Well, this is more common to me, at least. All three names mean identical things. So latent root, characteristic root, or eigenvalues all say the same thing. Here's the idea in plain English. For a square matrix A, we build a special equation called a characteristic equation, where the equation is this. So is it a determinant A minus this constant multiply with identity vector, or what was it? It was a 1 1 1 wala vector in matrix na. 0 1 0 0 0 1 0 and 0 0 1 matrix, identity matrix. Yeah, so this lambda is just an unknown number we are solving for, like x in a normal equation, so we solve for it. Okay, and I is the identity matrix, a matrix with ones on the diagonal and zeros everywhere else, like the number 1 but for matrices. And this just means take matrix A, subtract lambda from each diagonal entry, then find the determinant of the result. Okay, so this is basically the determinant modulus looking thing. Okay, so the roots solution of this equation are called characteristic roots, latent roots, or eigenvalues. Fine. So definition to memorize for define characteristic roots roots questions. The characteristic roots or latent roots or eigenvalues of square matrix A are the roots of its characteristic equation. Fine. So step 4, the real question, prove that 0 is a latent root of A if and only if A is singular. So if A is singular, then determinant is 0, then what? If its determinant is 0, then what? If and only if means we have to prove it both ways. That is, if 0 is a latent root, then A is singular. If A is singular, then 0 is latent root. The prove that 0 is latent root of A if and only if A is singular. But this case only exists with this case. Okay, so but actually here's the secret, both directions collapse into literally the same one line calculation. Let me show you proof. The characteristic equation is this. Now substitute lambda equals 0 into this equation because we want to check is 0 a root. So 0, so the question, yeah, 0 is a root. So the question is lambda equals 0 a root of the characteristic equation becomes exactly the question is determinant equal of this matrix equals 0. That's it. That's the whole proof. Let me write it cleanly. That was so plain or simple anyway, so let me write it clearly. So if lambda equals 0 is latent root of a, by definition of latent root, plugging lambda equals to 0 into the characteristic equation, it satisfies. Then A is singular because by definition of singular matrices, if determinant of a matrix is 0, then it's called singular, right? So hence proved. 2 marks in the bag. This is literally 4-line answer once you know it. Okay, so step 5, bonus proof that shows up twice. Proof adjacent of a non-singular matrix is adjoint of non-singular matrix is non-singular. I forgot even what adjoint is. Adjoint. Anyway, so first, what's an adjoint? You don't need to calculate it here. Just know adjoint is another matrix built from A called the adjugate. The important fact you need, just accept this as a tool, don't derive it. So A dot adjoint of A equals determinant of A times the identity matrix. This is a standard identity, just memorize it, it's used everywhere. Fine, so prove that adjoint A of A is non-singular when A is non-singular. Take determinant of on both sides of this. So we are taking this equation and we are taking determinant on both sides. Then by using the rule that determinant of x and y equals determinant of x times determinant of y, determinant of a product equals product of determinants. Then this transforms into this. A times the determinant of A times determinant of adjoint of A equals A raised to the power n. But y raised to the power n. Here n is the size of matrix. Example 3 for 3 by 3 matrix, because when you multiply a scalar into an by an identity matrix and take its determinant, you get this. So basically it's another mathematical fact that I need to memorize. What the hell, I don't want to memorize these things. Anyway, so since A is non-singular, we know this is not equal to 0. But how do we know that? Because when you multiply a scalar into an identity matrix, this is not equal to 0, so we can divide both sides by this root, this determinant of A. So we are assuming it not to be equal to 0. Prove adjoint of non-singular matrix is non-singular. So we are considering it to be non-singular, so that is why this is not equal to 0, so we can divide both sides by this determinant of A. Since determinant of A is not equal to 0, then this is also not equal to 0 and minus 1. But what if it was 1 minus 1, and then it becomes okay, fine. So adjoint of A is not equal to 0. Because this is not equal to 0, then this is also not equal to 0. Then the adjoint is non-singular. A little tricky, but fine. Okay, so bonus notice, this also proves another recurring question. Prove that these are equal. So that's literally the line right above. 2 questions, 1 proof. So what did we do here? Let's try this again. So we needed to prove adjoint of non-singular matrix is non-singular. So adjoint of non-singular matrix is non-singular. So we take a non-singular matrix. So A is a non-singular matrix, and we use this identity. We take determinant on both sides. Taking determinant on both sides, then we use this fact to separate those, and we use another mathematical fact. This was new and weird to me, and I need to look it up. Anyway, so using this fact, we can replace this part with this now, and then we can divide both sides by determinant of A, because apparently determinant of A is not equal to 0, so this is allowed. Then adjoint of A comes out to be equal to this, and if this is not equal to 0, then this can't be equal to 0, then this is also not equal to 0. Fine, recap what to remember for exam. Singular equals determinant is 0, latent root is root of this characteristic equation, eigenvalues or characteristic roots are the other names. 0 is latent root, A is singular. Just plug in lambda equals 0 and becomes this, and another proof. So these two proofs, and we are done with topic 2.